Hello and welcome to another session in physics. In this session we will be looking at the topic convection in gases. Convection in gases. But before that, let us review the previous lesson. Welcome back. At this point, let's talk about convection in gases. You would note that in our last class we talked about things like sea breeze and land breeze, and we talked about how convectional current is being set up. Convectional current is being set up between the sea breeze and land breeze itself. So we said that during the hot period, that is during the daytime, it seems like the ground or the land, which is a very good absorber of heat, tends to retain the heat it has absorbed in the daytime. So because of that, the air on the land is much more warmer, and because this air is warmer, warm air rises up, and cold air from the sea, which has a higher specific heat capacity than the land, would actually replace that warm air that has risen up. So for this reason, people who go to the beach feel colder in the afternoon as a result of sea breeze. At night, this process is reversed and roles are reversed. So this time around at night, because the sea has a higher specific heat capacity and it has the ability to retain heat more than the land does, because of this, the water in the sea is much more warmer at night. So the sea feels warmer than the land. Because the sea feels warmer than the land, and the land is now colder at night because it has lost all the air that it's stored since there is no more sunshine. The warm air on the sea has to go up, and the cold air from the land now has to take the place of that which is on the sea. So that's what we call land breeze, breeze that flows from the land to the sea. So at this point, let's now go to what we have today, which is convection in gases. The application of convection in gases is, we can see it in the construction of chimneys in our kitchens. Chimneys are those little openings at the roof of kitchens that help to allow smoke escape. That works in the principle of convection because smoke is a gas by itself. We also see it in the ventilation system of industrial buildings. Ventilation system of industrial buildings. You go to big restaurants, big supermarkets, big shopping centers, you see that the roofs are actually very, very high. They are raised so high up to improve the ventilation system so that warm air rises up. When warm air rises up, cold air can circulate at the bottom. This is essential to avoid overheating as a result of the huge population of people that troop to such places each day. We also have bonfires to work on the principle of convection or convectional current. We also have room radiators. When room radiators are in use, hot air rising from it can produce what we call a shadow in the room. It can produce a shadow in the room as a result of the sun. This shadow is caused by the sun due to convection also. And then we also have the one we call the glider lift. The glider lift is used in aircrafts. Yes, it is used in aircrafts. It is also used in flying sports where people have to fly up, probably high sea diving and other things. So this is done by positioning the aircraft toward the roofs of factories, where air is much more warmer. And because of the warmth of this air, the rising convectional current that has been set up is called thermal current. The next one is wind. It might interest you to know that convectional currents in air come when hot air rises from the equator and is replaced by denser air from the Earth's polar region. Remember, We have the polar regions in the Earth, and we have the equator, which is much more hotter. The equatorial regions are much more hotter, but the polar regions are much more colder. So when hot air rises from the equator on the Earth's surface, it becomes immediately replaced by colder or denser air from the polar regions. And this depends much to a large extent on the Earth's rotation about its axis. Apart from the Earth's rotation, it also depends on the large masses of land. Large masses of land and sea over which it passes, and their temperature as well. So the square area of the land and the temperature of that place as well. And then the seventh situation, or the seventh where we see convection in gases, is in air conditions. Air conditions. Air conditions are placed at the top of walls in rooms and not on the floor. Have you ever wondered why that is so? They are placed at the top and not on the floor. Not on the floor. Well, the reason for this is because hot air, which is less dense, rises up. Always remember that hot air always rises up. And because hot air rises up, less dense air, which is cool, replaces it at the bottom, which produces this sensation of coldness and cooling of the room and those who stay in it. That is as a result of convectional current that has been set up. If you're in an area where a tear gas has been spread, the sure way for you to escape without harm is for you to bend down very low. When you bend down very low, you're able to escape the conventional current that has been set up by this gas, because definitely the gas will rise up due to the Brownian motion and the random movement of its particles. So when you bend down or lay down low, you come down below the level of the tear gas and probably nothing would happen to you. At this point, let's talk about radiation. Radiation is the process by which heat is transferred or conveyed from one point to another without heating the intervening medium. Process by which heat is transferred or conveyed from one point to another without heating the intervening medium. It means that there is no intervening medium required for radiation to take place. Radiation moves through space. So unlike other methods where molecules are involved for heat to be transferred, in radiation molecules are not involved. This is because, like I earlier said, radiation does not require a material medium in order for heat to be transferred. That is exactly the method through which sun reaches us. And the energy that has been given out by the sun is what we call radiant energy. And the heat from the sun is known as radiant heat. There are times when this energy displaces electrical and magnetic properties. When this radiant energy gives out electrical and magnetic properties, it is said to displace what we call electromagnetic radiation. And electromagnetic radiation, we give it a name, which is what we know as infrared. Infrared. So put simply, infrared is what is produced when heat energy from the sun or radiant energy displaces electrical and magnetic properties, which results in electromagnetic radiation. There are about 3 instruments that we can use to detect radiation. The first is the one you can see on your slide here. This one is called a radiometer. Radiometer here. So it can be used to detect the presence of radiation. Inside you can see a tungsten filament, and then you can see some leaves that will be able to either diverge or converge when they are in the presence of radiation. A second instrument that can be used to test for the presence of radiation is what we call a thermopile. Thermopile is what you can see here on your screen. It is made up of a thermal resistance layer and a heat flux that helps us to note when radiation is available in the system. The third instrument we use to detect radiation is this, which you see here. It's called a Leslie cube. Leslie cube. At the tip here you see the crown, the cork, which is used to test for the presence of radiation. Notice here on the slide that it says dark surfaces are good absorbers of heat and they are poor emitters of radiation. Have you ever wondered why you feel hot when you wear a black cloth? You feel hot when you wear a black cloth because black tends to absorb heat, but they are poor emitters of radiation. That is why black is used to produce the effect of what we call tinted glasses, because they are very excellent reflectors. Heat and energy from the sun, solar radiation bounces back off them, so they are poor emitters of radiation, but they are good absorbers of heat. So because they are good absorbers of heat, it is not advisable for you to wear black on a hot sunny day. However, highly polished surfaces are good emitters of radiation and they are poor absorbers of heat, as we'll see in the following slides. So like we said, it's very wrong to put on black on a hot sunny day because you end up sweating and feeling hot, because black is a very good absorber of heat. On the other hand, we say that coated or highly polished surfaces are good emitters of radiation and they are poor absorbers of heat. That explains why aluminium roofs in our houses, they are well coated. When they are coated, it helps to keep the internal structure of the house as cool as possible because it reflects heat away and they are poor absorbers of heat. Also, it is good to paint your house white. When you paint your house white, remember that white is a color that does not really absorb heat. A house that is painted white will feel much cooler than a house that is painted black on a hot sunny day. The same principle is applied to cooking utensils. Cooking utensils are darkened at the bottom. When you go to a shop to get some frying pans, as you can see on the slide here, you've noticed that they are polished black at the bottom, and at the upper surface they are kind of polished with bright colors. The reason for making the bottom black is so that it will be able to absorb heat and make whatever it is you use it to cook to get done faster. The blackened surface will allow heat to go in comfortably, while the silver surface will not allow the heat to go out or escape. Remember, silver surfaces which are inadvertently white are not good absorbers of heat, so they tend to make heat bounce back off them. So the silver surface will not allow heat to go out, but the black surface allows heat to come in. So these are practical applications of radiation in our various houses. We also have the thermos flask. The thermos flask is used to keep the temperature of its content constant. You would notice that a thermos flask is polished silver white color. This is so that it will not allow heat to escape from it. And that is why at any point in time when you open this thermos flask, its content is always warm or as hot as it was when it was freshly put in. The features of a thermos flask are as follows. We have the cork stopper, which prevents heat loss by conduction, convection and evaporation. And we have the vacuum in the double wall, which helps to reduce heat loss or heat gain by conduction and convection. We have the silvered wall surface like I talked about, which helps to minimize heat loss by radiation. And we have the cork support, which helps to prevent heat loss by conduction. Another name for the thermos flask is the vacuum flask. So at any point in time, if you don't want to call it the vacuum flask, you can call it thermos flask. And that is it for the applications of radiation. Thank you for joining us in this lesson. To refresh your memory on what we've just discussed, please take the test that will appear on your screen.